Thank you for clicking on this video. Welcome to Hamamatsu YouTube channel. Many of you in photonics industry may know about Hamamatsu Photonics for our detectors. But we also offer many other products, including image sensors and cameras. In this 15-minute video, we will introduce a lineup of InGaAs image sensors and modules built around these sensors. I will also demonstrate how to acquire image data and measure the signal-to-noise ratio by using our software tools.
Oh, hey Lou. How you doing? Sorry, are you filming? Actually, I have some questions about image sensors and cameras.
Hi, Amber. Sure. What are you working on recently?
So actually, we just got a customer request. Our customer is looking for an InGaAs image sensor up to 2.6 micron. Currently in the marketplace, there are only a couple options, including MCT, which is brittle and really hard to handle, and also Type 2 superlattice, which has really poor spectral response rate at the longer wavelength. I know InGaAs image sensors are really good up to 1.7 micron, but do we have any other options from 1.7 to 2.5?
Oh, this inquiry came in at a good time. We just released the new area InGaAs image sensors with cutoff wavelengths varying from the standard 1.7 micron to the extended 2.6 micron. This product line features 20 micron pixel pitch, QVGA pixel format, and a 2-stage TE cooler. This sensor product line can achieve 500 frames per second by reading out from the 4 output ports in parallel. If higher frame rate is required, the partial readout in the single output port mode can be used.
That sounds great. Actually, it's good to know that we have multiple options from 1.7 to 2.6 micron. And also the high frame rate and low noise is very suitable for machine vision.
Mm-hmm.
So does Hamamatsu provide any other solution outside of detectors for our customers? As you know, nowadays, customers have very lack resource for their in-house design, or even before they want to confirm their design, they want a kit or a demo for the evaluation. Could Hamamatsu provide anything like that?
That's a good point. In addition to the area InGaAs image sensors, we also released the camera modules featuring these image sensors. So now customers can purchase the camera module with the sensor built in, and the sensor customization, the module customization are also available per customer's request. These newly released image sensor modules are incorporated with the USB 3.1 interface and can work with our standard DCAM API and associated software toolbox. We have designed this software API to standardize camera control and the functionality of all Hamamatsu digital cameras. DCAM API is responsible for connecting all registered camera modules to the host application. So our software engineering group in the US can support any software issue and also support customers who build their own application software based on the SDK that we offer. I will show you how to set up the sensor and collect the image data by using 2 different application software, SCAP4 and HCImage. It's as easy as plug and play. In the package, you will find 1 power cable, 1 USB 3.1 cable, and the camera module with the sensor built in. In the front of the module is the C-mount. Users can put on their own lens on top of the sensor. And today, I won't use any lens. I will take the dark image by putting on the cap, and take the signal image by taking the cap off. In the back of the camera, there is 1 power port, 1 USB 3 port, and 2 SMA ports. 1 SMA port is for the trigger in, which is to control the exposure of the sensor. The other one is for future extension.
That looks really good.
Now let me show you how to install the software. You can download the latest DCAM API from our website, dcam-api.com.
In the installation package, you can find the setup.exe file. Double-click this file. You can open the DCAM API setup window. Here you can find the USB camera. Click this button to install the driver.
Now let me connect the hardware. First, to connect the power cable. Then connect the USB 3 cable. Please make sure your computer supports the USB 3.1 interface.
After install this USB driver, you will see in the device manager, the Hamamatsu image sensor module now is working properly. Let's go back to the DCAM API setup window. Click Tools. Here you can find the XCAP4 software. Click this button to launch XCAP4. This is a lightweight image acquisition software. Click Property tab. Here we can set the sensor properties. This sensor has 2 readout speeds. At speed 1, the sensor is operating at a single output port. At the readout speed 2, the sensor is operating at a 4 output port. And the sensor also can be triggered by internal trigger and external trigger. This sensor has a 2-stage built-in TE cooler, so we can set the target temperature to be -20, which is the lowest temperature that the sensor can go down to. The exposure time can be set from 1 microsecond to 5 seconds. Here we can set it to be 1 millisecond, so we can see some light response from the sensor. This sensor also can be operated in the partial readout or the full frame mode. So here we are running at the full frame mode. Let's check periodically update value, so we can monitor the temperature periodically. The image can be acquired in 2 modes. One is continuous, the other one is snap. So at the continuous mode, I'm waving my hand on top of the sensor, so you can see the image is changing in real time. At the snap mode, we can capture one image and save it to the .img file. And in the target directory, you can find the saved img file. The DCAM API toolbox also offers the img to TIFF file converter. So after you convert the img file to TIFF file, you can do any image processing by using a third-party tool.
Wow, this looks so easy to use. But what if the customer wants to do some more complex procedure than acquiring an image, such as evaluating the sensor by signal-noise ratio? How are we going to do this?
This is a good question. The signal-to-noise ratio measurement is a must when you evaluate a sensor or a camera. This is a test procedure that we usually use to measure the SNR. To calculate the SNR, multiple frames need to be collected, and the dark subtraction needs to be conducted on each frame. Then the standard deviation can be calculated from the dark subtracted signal frames. So the lightweight software XCAP4 is not the best tool since it does not have the NIR image processing capability. I would recommend using the HC image software for this type of complicated test procedure. But please keep in your mind, HC image is supported in the US and Canada only.
You can download the latest HC image live from our website, hcimage.com. Please remember to register before you can download. In the installation package, you can find the HC image live install file. Double-click this file to install the software. After the installation, the HC image live icon will show up on the desktop. Double-click this icon to launch HC image. In the HC image live, you can see the part number of the image sensor module shows up here. The image can be acquired in two different modes, the live mode and the capture mode. This sensor has a built-in two-stage T cooler. We can set to turn on the cooling function and set the target temperature to be -20 degrees C, which is the lowest temperature that the sensor can be cooled down to. Let's set the minimum integration time so the maximum frame rate can be achieved. Now the sensor is running at the full frame. This sensor has two readout speeds. At speed 1, the sensor is being read out from one single output port. At speed 2, the sensor is being read out from 4 output ports in parallel. Let me select the speed 2 here, and also select the internal trigger. So the trigger function will be generated on the module at the internal trigger mode. At speed 2, the maximum frame rate around 500 frames per second can be achieved at the full frame. You see here. Now let me select the speed 1. Also at the full frame. About 150 frames per second can be achieved at speed 1. And at the speed 1, the partial readout is available. If I select the half of the image, you see the frame rate is about doubled. Okay, let me go back to the full frame and speed 2. Let me show you how to save the dark reference image. Let's save the dark reference image at the 100 frame rolling average. And change the integration time to be 1 millisecond. Now let me put the cap on the camera so we can collect the dark image. Okay, this dark reference image is collected. Now we can use this dark reference image to do the background subtraction. Then open the cap on top of the sensor. Let's go to the sequence. Save the signal frames into the CXD file. And set the signal frame to be 100 frames because we would calculate the standard deviation and the mean across these 100 frames. Let's press start. Okay, now we collected the 100 signal frames with the dark subtraction. This is the CXD file for these 100 signal frames. We got 100 field data. Let's go to Analysis. Select Sequence Intensity Analysis. This is the data2.cxd file that we just collected. Let's draw the area that we would like to analyze. And select the measure. We would like to calculate the mean and the standard deviation so we can calculate the signal to noise ratio across these 100 signal frames. Here is the summary of the statistic data. So the mean of the mean and the mean of the standard deviation is being calculated. We also can copy this measured data into Excel. So this is the number of the signal to noise ratio that we want to calculate.
Thank you, Lou, for introducing this significant 2D InGaAs image sensor module and the image acquisition tool. Actually, this 2D InGaAs image sensor is not only suitable for image acquiring, but also good for hyperspectral imaging. Their capability to detect extended wavelengths can help identify compounds that couldn't be detected using wavelengths shorter than 1.7 micron. Plastic sorting, geology survey, and pharmaceutical industry could all benefit from this feature because many man-made materials, mineral resources, and chemical compounds could be recognized in the near-infrared region. Also, the image sensor's high frame rate could translate into high throughput, suitable for those applications requiring high speed, such as inline process or surveillance. If you don't need that much resolution, it could turn out to be actually even higher speed because of the partial readout feature. The module and image acquisition tools enable an easy implementation for different systems without customers spending a lot of resources developing a dedicated system before the evaluation. Even after the evaluation, customers could implement this module to save them time and money for the sensor electronics and freeing their resources for other development works.
As you may know, near-infrared imaging not only can be built from a 2D InGaAs image sensor, but also can be built from a linear InGaAs image sensor, which is operated in the line scan mode. We will introduce a high-speed linear InGaAs sensor and a line scan camera in another video.
If you have any interesting ideas, questions, or comments, feel free to reach us at hamamatsu.com.